Hello, class of Physics 7C. Today we're going to talk about Chapter 11. So we're going to talk about a new different aspect of equilibrium. Basically, in the previous chapters, we consider equilibrium of a point object, and in this one, we're going to talk about um the equilibrium of extended bodies. So we're going to learn the condition that must be satisfied for an extended structure to be in equilibrium. We're going to learn about center of gravity. We're going to learn about how to solve the problems that involves rigid bodies in equilibrium. Okay, so we've devoted a great deal of effort um, to understand why and how body accelerating responses to the forces acting on them. But very often, we're interested in making sure that the objects or the bodies don't accelerate or they don't move. For example, if we have a ladder, right, that lean against a wall, right? We want to make sure it doesn't fall down, right? So when you're climbing this ladder, right? So, for example, we have crane, right? Right. This is when it is hoisting, um, half a ton of or a tons of full bucket of concrete. We want to make sure that it doesn't fall down, right? These are the things we're going to talk about, how to keep these extended structures in equilibrium. Okay, so we've learned in chapter 4 and 5 that a particle is in equilibrium, and that is basically the particle doesn't accelerate if the vector sum of all the forces acting on the particle is zero, right? So for an extended body, the equivalent statement is that the center of mass of the body has zero acceleration if the vector sum of all external forces acting on this body is zero, right? So this is often called the first condition for equilibrium. Okay, so this is the first condition, right? So basically, all the forces in its vector sum, that's the net force, acting on this extended object, need to be equal to zero, um, right? So in order um, for this object to be in equilibrium. However, um, because in this lecture we're going to talk about extended bodies. There's a second condition for an extended body to be in equilibrium. That is, the body must have no tendency to rotate. Okay? This condition is based on the dynamics of rotational motion. It means that the sum of the torques due to all the external forces acting on this body must be zero, right? That's the second condition. The sum of all the external torques must be zero about any point, right? So, and that is basically the second condition. So, basically, different from considering point object, when we're talking about an extended object, for it to be in equilibrium, the body must have no tendency to rotate. So basically, in this chapter, we'll apply this first and the second condition for the equilibrium um, to the situation in which a rigid body is at rest. There's no translation or rotation. If this condition is met, we said such a body is said to be static equilibrium. But the same condition apply to rigid bodies in uniform translational motion and without rotation, such as airplane in flight with constant speed and direction and altitude. Such a body is in equilibrium, but it is not static. Okay, but in this chapter, we're going to primarily focus on basically talking about the static equilibrium of a rigid body. All right. Let me give you a couple examples where um, the two conditions are applied to a rigid body in order for us to determine if this object is in equilibrium or not. For example, what's shown here is basically a disc, right? And there are two forces that apply to it on the two opposite rims. The two forces have the same magnitude, except that the direction that the two forces point to are opposite, right? So in this case, the net force is exactly zero because the two forces cancel out. So if you look at the center of mass of this extended body, there's no tendency for the center of mass to move. However, when you look at the second condition, that is whether this object has any tendency to rotate, then you will find there's actually a net clockwise torque about the axis, right? This basically this torque is going to accelerate this in the clockwise direction. This torque is going to accelerate in the clockwise direction as well. So this body will not be at rest because it will start rotating in the clockwise direction, right? So let's look at this. Here's another example, right? So in this case, what you see is because the two forces apply to this object, they're pointing in the same direction. So we immediately know that sum of all the forces is not going to be zero. So there is a net upward force, so the body at rest will start moving upward, right? The center of, right? That's and also in this case, if you look at the torque that has been applied to this body, the net torque about the axis here, right? If there's an axis that basically go out of the plane from here, this net torque is zero, right? So basically, we have this this force that's basically giving you a counterclockwise torque, and you also have the second force, this force, and that give you an anti-counterclockwise torque. So the two torques actually cancel out. So this body at rest has no tendency to start rotating. So this is a second example where it shows that the first condition is not met, but the second condition is satisfied. Basically, this whole extended object will start translating, but it will not rotate. Right? Here's the condition where both conditions are actually satisfied if you analyze all the forces applied to it and the torques applied to it, right? If you look at the forces, right, you have two forces that's add up to 2F pointing upward. You have another force that actually that's running in the opposite direction, that's pointing down, right? And this force of the three forces that cancel out. So basically the net force is equal to zero. So the body will not start translating, right? And the second condition, that's we're looking at the net torque, right? Around this axis, right? The 2F pointing down has zero torque, right? And this force and this force, they give one of them give a clockwise torque and the other gives a counterclockwise torque, and so these two actually cancel out with each other, right? So this is the condition where both the first and the second condition, basically the first condition is sum of all the forces, the second condition is sum of the torques equal to zero, right? So again, for an object to be in equilibrium, you need to have both the force and the net force and the net torque to the vector sum of them that need to be zero. Okay? Okay, so the next concept we're going to talk about is center of gravity. So in most equilibrium problems, right, um, one of the forces that acting on this body is its weight, the gravitational force. We need to be able to calculate the torque of this of this force, right? The weight doesn't act at a single point. For example, for such an extended object, you basically have forces, these weight forces that's a result of the gravitational force from all little point, right? Basically, we need to be able to calculate the torque of this force in a simplified manner. Otherwise, we have to integrate all of that every time. So the weight doesn't act at a single point. We know that it is distributed over the entire body, but we can always calculate the torque due to the body's weight by assuming that the entire force of gravity, or the weight, is concentrated at a point called the center of gravity. Okay? Right? We basically can treat a body's weight as though it acts on at a single point. That is the center of gravity. Typically, we use CG to denote this point. Okay, the acceleration due to gravity decreases with altitude. We know that, right? If you're far away from the surface of Earth, right, your G decreases, right? On the surface, on average, it's 9.8 meter per second squared, right? If it is further away, the higher the altitude, right, the further away you are from the Earth, this G just decreases, right? But if we can ignore this variation over the vertical dimension of the body, then the body's center of gravity is identical to its center of mass, right? So the center of mass, we typically denote it as cm, right? Okay, just to give an example that in most cases, these extended objects that we talk about, really we can basically say the center of mass is equal to center of gravity. Okay, here's an example. This is a really high tower that's actually 452-meter tall, in Malaysia. And the thing is, the center of gravity, right, the CG of this tower is only 2 centimeters below the center of mass. Okay, please remember this is a 452 meter, right? That is 400. That's 45,000 centimeter, right? We're talking about the CG minus a centimeter of the height of this is only actually the difference of the two is only actually a negative 2 centimeter, right? So that's a very small difference. So basically, when we're talking about center of gravity, um, in almost all situations and cases when we talk about this, you can assume that the center of gravity is the same as the center of mass. Okay, so we just talked about that we can view that the weight that's actually distributed over the entire body can be think of as it was concentrated on a point on at the point that's called the center of gravity or the center of mass. So we're going to prove that the torque actually applied by this distributed force versus this concentrated force that's on the center of gravity, they actually give exactly the same torque. Let's first review what a center of mass is, right? So in the previous chapters that we defined, the center of mass is m1x1 plus m2x2 plus dot 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 divided by m1 plus m2 plus all the masses in this. Basically, this is a weighted sum um, of all the x positions of all these object, right? And for the y position of the center of mass, that basically m1 y1 m2 y2 dot 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 divided by m1 plus m2, right? right? That gives you the y coordinate of the center of mass. And you also have z, right? That's m1, z1, m2, z2, right? This will give you the z coordinate of the center of mass, right? All right. So basically, with this, this is a if we write it in the full vector format, that will be m1 r1 plus m2 r2 plus m3 r3, m1 plus m2 plus m3, dot, dot, dot. Sum over I, mi, ri. This is a vector sum, remember that, right? This is give you what the center of mass is, right? Okay, now let's consider the gravitational torque on a body of arbitrary shape, right? Okay, so basically, let's first, assume, this object is composed of a series of little masses, right? And each of this mass has a weight that's migi, right? And the torque applied by these little masses, right? Torque I is going to be Ri, right? Cross product with weight I. Let me rewrite this. It's basically Ri cross products with weight I, right? That will be Ri cross product with Mig, right? Okay, then the total torque, right? The total torque of the system will be sum over all the torque I, right? From each individual weight, gravitational force of each individual object, sum over all of them, right? And let's pull the mi, ri out, right? So basically here we have m1 r1 plus m2 r2 plus dot 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 g. And equal to sum over I, mi, ri, cross product with g. Okay? So then when we redefine a new constant that's called the big M, that basically is the sum over all of the small masses. That will be the total mass of these, okay? Then if we do a division of this, what we do is this. I will show you. The total torque is equal to sum I, mi, ri, right, divided over by sum I, mi, right? And then we multiply this thing back here, right? And that's equal to the big M, right? Right? And then we still have this G here, right? Remember, that's basically this equation, and we have G here, right? So basically, let me write it out cleanly. Divided by time mg, right? So do you recognize what this is? What is this? Right? That's basically, if we go back and look at this equation, we know the sum over mi times the r vector divided by the sum of the mass, that would just be, this would just actually be the center of mass position, right? So now we basically know the total torque applied to an object that has a series of mass in it would just be like if this the weight is concentrated on the center of mass position, right? That's basically with basically with this equation that we just show just now, the proof. With that, we basically prove for a given extended object, right? And you for a given any given point or a given axis, the torque due to the gravitational force that's pull on this extended object, m over g, right? So it's actually a series of small masses, right? Delta m over g. You basically sum of all the torque together is equivalent to if the lever arm is basically RCM from your axis to the center of mass position, and cross product with the total force, the total gravitational force concentrated on the center of mass location. Okay, right? So this is basically a simplification of that, right? Even though you have an object that have all the mass distributed everywhere in the entire body, right? You can actually view that everything that due to the gravitational force would be like concentrated on the center of gravity or center of mass. These two are equivalent in most situations. And then you just find how far this center of mass is away from the axis. That would be your lever arm, right? And you do a cross product. That would be the total torque. That would be the torque. Sum over all the I torque would be equal to the RCM, right? The position from the axis to the center of mass, cross product with the total weight of this object. Okay, so we just proved that to show that's the case. We just talked about the importance of knowing the concept of center of gravity. So how do we actually determine or finding the center of gravity, right? So we've used in the previous lectures, we often use the symmetry consideration to locate the center of gravity of an extended object, just as we did for the center of mass. The center of gravity of a homogeneous sphere, cube, or circular sheet, or rectangular plate, it's at its geometric center. The center of gravity of a right cylinder or a cone is on its axis of symmetry, right? This is basically, we've always basically learned that, right? That this will be C of G of a disk, right? And for a body with a more complex shape, right? So we sometimes and locate the center of gravity by thinking of the body as being made of symmetrical pieces. For example, we could approximate a human body, right, here, right, as a collection of solid cylinders, right? The arm is a solid cylinder, right? The body, the trunk is a solid cylinder, and your legs are solid cylinders. Then we can locate the center of gravity of these little solid cylinder pieces, and then we basically use all these individual pieces, these M1, M2, M3, M3, M4, and we basically use all of these to actually determine the center of gravity for a complex shape. And there's another way actually to experimentally determine where the center of gravity of a complex shape project is. Say, for example, this mug, right? When this mug is acted on by gravity, it's supported or suspended at a single point. For example, this hand is holding this mug suspended at a single point. Then the center of gravity is always at or directly above or below the point of suspension. Basically, vertically, your center of gravity will sit on this line. Okay, this is the line where the center of gravity sit on, right? Okay, and you can actually choose another suspension point. For example, we have this here, we can choose a suspension point. Then you can find another line where the center of gravity sit down, and then basically you have two lines, and where they cross each other, that would be where your center of gravity is. Okay, so that's basically we can use the fact that with a single point of a suspension with support, the center of gravity always go through this vertical line through this, right? The reason is that if it were anywhere else, the weight would have a torque with respect to the points of suspension. And then this body would not be in rotational equilibrium, will start rotating. So, right? So basically, when you do this kind of suspension, this object, this mug, would be in static equilibrium, then you know that this center of gravity must be sitting along this line of this line that go through the vertical line that go through the point of suspension. Okay. Okay, so we've just talked about when a body is acted on by gravity, is supported or suspended at a single point, the center of gravity is always at or directly above or below the point of suspension or the point of support. If it were anywhere else, right, the weight would have a torque with respect to the point of suspension or the point of support. The body would not be in rotational equilibrium. It will start tipping over, rotating or tipping over, right? So we use that to actually basically, we can use that to determine the center of gravity for an, say, for example, of irregular body like this mach here, and use the same reasoning. We can actually see a body supported by several points must have its center of gravity somewhere within the area bounded by the supports. Um, this explains basically this explains why a car can drive on a straight but slanted road. Basically, this road if it basically inclined at an angle, right? And that's a slanted road, and your car is basically driving or parking on it. And your car wouldn't tip over if this angle is not very large. And that's basically your center of gravity actually will fall between the area of support. The area of support would be the force support point that's basically between all the contact points of your wheels, right? However, if the angle is too steep, right, in this case, right, in this case, if the angle is too steep, right, if it's too large, then your center of gravity actually falls outside the supporting area, right, and then the total weight of this object is going to be outside this, and then the car will start tipping over. Basically, around this point of the support here, right? This is a point of support. You can look at the total torque around that, right? This car will start tipping over because of the weight of this object, right? That is why for a truck that has a high center of mass, right? It is much higher than a regular car. It's much higher up from the road, and it will be much easier for a truck to overturn on a highway. You would just need a much shallower incline, right? Much smaller theta for this center of gravity line to fall to lie outside the area of the support. Okay, in that case, the truck will start to tip over. So um, basically, if you see a truck that overturns on a highway and blocks the traffic for ours, it is really the high center of gravity that's to blame. Okay, this actually does not only apply to a truck, it applies to SUV as well. Those cars that have higher center of gravity. Okay, so basically, the lower the center of the gravity and the larger the area of support, the more difficult it is to overturn a body. Okay, right? That's basically um, so. What we've learned from these slides. Okay. Okay, so now let me give you an example where you can actually apply what we just learned. Basically, you want the line of center of gravity to fall between the two to fall between the supporting area for an object to be in static equilibrium. Okay, so here's an example. Basically, we have a uniform plank that has a length of L that is 6 meter. So we have a plank here, right? 6 meter long, right? And the mass of this is it's 90 kilogram, and they're actually it is sitting on two sawhorses, right? You have two sawhorses that they are a distance d separated from each other, right? The and they're equidistant from the center of the plank. Okay, so basically this is the center of the plank, and we have this a guy that wants to stand on the right end of the plank. So we have a little young guy here sitting here who has a mass of m, and we want to know if the plank remain at rest. So basically, it doesn't tip over. How massive can our little guy be? So it doesn't tip over. Okay, right? So this is exactly where we can actually apply what we've just learned, right? If you look at basically this system again, right? So basically we have this plank here, right? This 90 kilogram, and this person sitting at the end, right? We have two supporting point, right? This is the areas of support. So we both basically want the plank plus this person, the center of the gravity of these two together, to be sitting in between this support area, right? So that means to the extreme, you can be sitting here, right? This is basically half of d away from the center, d divided by 2. Remember that the distance between the two sawhorses is d, right? Okay, right? So now let's calculate what the center of gravity, basically CG, of this plank plus this human, this little boy, right? Okay, and we want that to be at d equal 2, right? Okay, right? So let's set up the coordinate system, right? So basically, we have an x-axis, and we put the origin here, right? That's just very handy way of choosing your coordination system, choosing your origin, right? Then we can calculate the x center of mass of the or center of gravity, they're the same, of the two, the plank plus the boy system, right? And what the center of mass for this plank is exactly at the center point of this plank, right? That will be at the x position. That will be the big M times 0, right? And then this boy is at the other end, is M times its distance from the 0 to here, and that will be L divided by 2, right? L divided by 2, okay? And divided by big M plus small m, right? So that would just be, right, M divided by 2 m small m times L, okay? That's the distance of the center of gravity, right, to the origin of this x-axis we set, right? So basically want this center of mass to be smaller than d over 2, right? that basically have m divided by 2 big M plus small m times L smaller by d over 2. Okay, right? So if we can write this out, ml small and the 2, they cancel out, right? M plus big M plus D, small m plus D, right? And then we basically have m times L minus D smaller than m times D, and basically m need to be smaller than big M times D divided by L minus D. Okay, then this is the maximum mass of this little boy can be. That would be the M max that the little boy can be, such that this plank doesn't tip over. Okay, this is one way of doing this example. Okay, there's actually another way of doing it. We can actually um, use torque to actually figuring out how to put this system in equilibrium. I'm gonna show this in the next slide. Okay, the second way of solving this problem is basically using the two conditions that we talked about before. That's basically you have the sum over the forces, right, equal to 0, and also the sum of the torque is equal to 0, right? That's what we talk about the first and the second conditions, right? Particularly, let's first look at all the forces, right? So basically, we have um, the weight of this plank, we have the weight of this person that's applied to here, right? For the plank, right? We're looking at the plank only, and also we have the normal force 1 and the normal force 2, right? So when this mass increases, or this weight of this person increases, when this force increases, what we're gonna have is that this force is gonna slowly go down, and eventually that's gonna be 0. And when it is 0, that will be exactly the point where the system will, if this increase a little bit more, then this thing will start tipping over. So basically, when this force is 0, we basically have three forces, right? And of course, N1 will be equal to mg plus mg, right? So basically, that's the case. And we would look at torque, right? The torque of this system, let's first analyze what is this lever arm, right? That's d over 2. What about this lever arm for this force? That would be L over 2 minus D over 2, right? So to balance this out, we basically need to have mg times D over 2 equal to mg times L over 2 minus D over 2, okay? Right? So that's the condition, right? We basically have m equal to, the g will cancel out, equal to m times D over, we can cancel out the 2 as well, L minus D. So as you can see, this will be exactly the same solution as we got using the basically the line of the center of gravity need to be within the areas of support. That's exactly the same as what we get here using the two conditions for equilibrium, right? That's expected, okay? Right? This is basically the second solution for solving this equilibrium problem. All right. So now let's look at the problem-solving strategy for static equilibrium. Okay. So what you need to do, you need to identify the relevant concept. That basically here we have the first and second condition for equilibrium. That is the forces, the net forces in both the x and y direction need to be 0, and also the total torque for any given point that need to be 0. So you can set up the problem by using the following steps. You first sketch the physical situation, identify the body in equilibrium to be analyzed. You draw the free body diagram, always do that, right? Showing all the forces acting on the body, and important that for analyzing rigid bodies, where the force exactly acted on, at which point it is acted on is really important. Show the point on the body at which each force acts, right? You choose the coordination axis that works in our favor, specify their direction, right? Specify a positive direction for rotation of rotation for torques, and choose a reference point for which to do to compute the torques. And you always want to choose the point where that works in your favor, so you don't have to do too much computation. Okay. So to execute the solution as the follows, you write the equations, right, according to the first and second equation, write them into separate equations, and then you obtain as many equations as you have unknowns, right? You have 3 unknowns, you need 3 equations. You may need to compute torque with respect to 2 or more reference point, depending on the situation we're dealing with, okay? And then you evaluate your answers, and then you can check your results by compute the torque, the total torque again with a different reference point, and just to see, given all the forces that you calculated, whether they will give you a total torque of 0 with a different reference point. And you should, because the second condition tells you if an object is in equilibrium, the total torque for any given point would be 0. Okay? So let me give you an example, right? So here's a wall, right? And you have a letter, right? That's here. And also you basically have someone that's standing on it, right? Okay. And its distance from the ending point here is L, okay? And the center of gravity, let's say it's here for the letter, and that is a big L away from this, okay? So the question, and this person has a weight of mg, and the letter has a weight of big mg, okay? So the question here is that what is the friction force that you would need to actually stop this ladder from slipping? And also another point I need to act is that this wall here is actually frictionless. So when this ladder is in contact with it, there's no friction, okay? Right, so let's first conceptualize the whole thing, basically draw the free body diagram, right, for this ladder, right? Okay, so basically because the surface of the wall is actually frictionless, you only have a normal force, right? And we call it N1, right? And also from the ground, right, you would have a normal force pointing upward, let's call it N2. And also this is the friction that we want to know as well. And also we have this person that's standing here, let's have mg. You also have halfway from this ladder that have big mg, that's the weight of this ladder, right? The distance here is small l, the distance here is big L, okay? And also another thing that I forgot to define is that this the top, from the top to the bottom, this distance is big H. That's a given quantity as well. So let's look at this. First, we want to use the first condition, right? So basically the forces in the horizontal direction need to be 0. What are the forces in the horizontal direction, right? So that would just be, let me write it out using a different color, right? That would just be this force and this force, right? The normal force from the wall and the friction force. So basically, if we define this as the positive x direction, that will be F minus N1 equal to 0, right? We also have sum over of all the forces in the vertical direction, right? If we define this as the positive y direction, then n2 minus mg minus big mg, that's equal to 0, right? And also another condition that we need to use is sum of all the torque. Okay, let's find a reference point. Okay, which reference point should we use, right? The easy one would be to use this one. Use this one because now we have the lever arm for this force, for the two weights, and also the lever arm for N1 is well defined. Okay, so with respect to that reference point here, this reference point, the torque would be, okay, let's say this direction is the positive torque direction. That will be mg times L plus big mg plus big L minus N1, because N1 is is a torque that's working against it, as in the counterclockwise this direction, time big H, right? That needs to be equal to 0. Okay, so basically with this we can calculate, right? So what is N1, right? N1 is equal to mg times L plus mg times big L divided by H, right? And then with this equation, right, we will know that F equal to N1 equal to actually M times small l plus big M times big L divided by big H times G. Okay, that will be the friction force, right? Okay, so that's basically how we actually calculate, the friction force for this ladder system. And that's the friction that's needed to actually stop the system from slipping. Okay? Okay, now let's look at another example. So in this setup, we basically have a uniform meter stick here that has the mass uniformly distributed along the long axis, and it is placed against a vertical wall, and also at one end is held by a lightweight cord that makes an angle with the stick. The angle is theta. Um, and also on the stick, there's a mass, a little mass of M that's basically hanging an X meter away from the wall. And also the coefficient of static friction between the end of the meter and the stick, between the end of the meter stick and the wall is 0.4. So basically, if friction force is needed to balance, to basically balance out all the forces and torques to make this stick in equilibrium, in static equilibrium, so there could be a friction force here. Okay, so this is the difference between this question and the last one we showed. So the question here is, what is the maximum value of the angle theta that I can have in order for the stick to remain in equilibrium? Okay, so in order to do this problem, let's first draw the free body diagram for it, right? Here's the meter stick, right? Let's magnify it, make it bigger so you can see. Okay, then let's draw all the forces that are exerted on this object, right? And first of all, we have this this weight, right, that come from the hanging mass, right? That is X meter away from the wall, from the left end, and we have this tension force that makes an angle of theta with the meter, and the meter, the total length of the meter, of the meter stick is 1 meter, right? Okay, and also we have another two forces. One would be the normal force that come from the wall that exerted on this meter stick, and also you have the friction forces that come from the wall as well. Okay, so basically here, whether the friction force will point upward or downward, we actually need to calculate it. But here, let's just assume that it's pointing up, right? Okay, so now let's also define what the x and y axis are. We define the positive x-axis pointing to the right, and the positive y direction is pointing upward. Okay, so now let's apply what we have learned. Basically, we need to use the two condition to calculate the two conditions for equilibrium to solve this problem, right? So the first condition that we will use, right, the first condition, that will be all the forces in the x horizontal direction will sum up to 0, and also for y, right, that's all the forces in the y direction will need to sum to 0. Okay, let's look at all the forces in the x direction, right? Along the x horizontal direction is relatively simple because we only have two forces. One is the normal force that point to the right, that's pointing in the positive x direction. And then we also have the tension force that its projection on the x-axis, right? That will be t times cosine theta, right? And that is actually pointing in the negative x direction to the left. So that is minus t cosine theta, right? And that basically will need to be equal to 0, right? And for the y direction, what are all the forces? And here we basically have the friction force that we assume is pointing upward, so we write a positive f here, and also we have a t times sine theta. That will be the projection, the y component of the tension force. That will be the t times sine theta. And also we have the weight, the mg, that's pointing downward, right? Then we minus that out, subtract that out. All of these will give you a 0. So what about, so we have all the forces, basically the first equilibrium condition that's written out here. What about the second condition, right? The second condition is that we need to calculate all the torques around any given point, right? And make sure that is 0, right? For this one, we can choose any reference point. It's in principle supposed to give the same result, right? And for here, we definitely want to choose a reference point that work in our favor. Basically, we don't want to, just place this reference point anywhere such that we need to calculate the torques from all these forces, right? So a natural choice is place it at one of the end of this object. Let's see if we place on the right end of this, right? Basically, we have, this is our reference point, right? With this reference point, because the tension go through this reference point, so it doesn't generate any torque around this reference point, right? Also, the normal force doesn't generate any torque, right? So automatically, by choosing this reference point, we already knock out two of the forces. Now we don't have to consider them anymore. And we have the other two forces, basically the friction force and the weight, these two that we need to consider. Okay, so basically around this reference point, let's get out the torque, right? So, and for the counterclockwise torque, the friction force is giving a counterclockwise torque, that will be F, and the lever arm here is basically the whole length of the meter, that will be 1, right? And what about for the weight, right? It's giving a counterclockwise torque, so that's why, and we have a negative sign here, and also the level r here, we need to calculate it. That will be 1 minus x, right? So times 1 minus x, that will be equal to 0, right? So these are the two conditions that we need to meet, right? And we have three equations. And how many unknowns do we have? We basically have, let me use a different color. We basically have the friction force is an unknown, right? And the tension is an unknown, right? And also the normal force is an unknown, right? Okay, so we have three unknown variables, right? And then we have three equations. So in principle, we can solve this if all of them are orthogonal. There are no degenerate equations. Okay, so let's work out the math here. Okay, all right. So with this equation here, we can already solve what the friction force is. Basically, we go here. The friction force is equal to, you move this to the left hand side, and that will be mg times 1 minus x, right? So we already solved this. This is the friction force, right? And now we basically want to calculate the tension and the normal force. Let's first calculate the tension. And then we can move that actually into the second equation. So we can see here, right, with this equation, right, we have the normal force is equal to T times cosine theta, right? And also with this one, we basically have um, the tension force, T times sine theta, is equal to mg minus f, right? And we already solved what f is. We move that here, right? That will be mg minus mg1 minus x, right? What is this? That will be mg times x. So basically we can solve what the tension is. That's mg times x divided by sine theta, right? Basically now we know what the tension is, right? We know m, we know x, we know theta, and then we basically can substitute this into here to find the normal force. Okay, the normal force will just be T times cosine theta equal to mg times x divided by sine theta times cosine theta, right? Then we move this down a little bit, mgx sine theta divided by cosine theta. We basically do a division on cosine theta from um, um, from the top and bottom. That will be given as mgx times tangent theta. Okay, right? So now we know f, right? And we know n, right? So let's look at what the problem asks, right? It asks what is the maximum value of theta that it can have if the stick is remaining equilibrium, right? What is the condition that can meet that, right? So basically, the maximum friction force would be equal to n times mu of s, right? So that means this friction force that we calculated need to be either smaller or equal to n times mu self s, right? So that means the friction force we've calculated above, right? That would be the mg 1 minus x, right? So basically f smaller than n times mu of s, right? That means mg times 1 minus x, right? That's basically this equation here that comes to here, right? And that would be need to be smaller than n, and that will be here, right? So that would be mgx divided by tangent theta times mu of s, right? So let me highlight these as well, right? So the n is equal to this, right? And n is here. So basically, this is the inequality equation that we're handling with, right? Then we move the tangent theta to the left-hand side. It need to be smaller or equal to, right? We cancel out mg here, smaller or equal to x divided 1 minus x times mu of s, right? So then that means the theta need to be smaller or equal to arctangent x times x divided 1 minus x mu of s. Okay? Right, that's basically the solution. Okay? So now let's review what we have done for this, right? We first draw the free body diagram here, right? So this is the free body diagram. And then we basically analyze all the forces that are exerted on it. And then we use the first and the second equilibrium conditions. The first one would be all the forces in the x direction and the y direction need to cancel out. And the second condition is basically given a reference point, any reference point, and here we pick one that work in our favor. That's the right end of this meter stick, and then we calculate all the torques, and they need to sum up to 0. Okay, and using these three equations, we can solve the three unknowns. Then after that, we basically utilize the condition that the maximum friction force is the normal force times the coefficient of a static friction. So that give us this inequality equation that the friction force we calculated need to be smaller than that, right? That basically allow us to solve this equation on a given inequality that shows that theta need to be smaller than the arctangent of this expression. Okay, so one of the things that we talked about is you can actually verify if you have calculated all the force correctly, right? So basically, here we first choose the right end as the reference point. What about if we choose the left end as the reference point? That's the second reference point. Would all the torque still balance out? So let's look at that for our new torque calculation. They're using the left end as our reference point, right? So let's see what all the torques. Now the friction and the normal forces, these two, they don't have any torque anymore. It would be the weight and also the tension, actually the upward tension force, the y component tension force actually have torque, right? So the weight here is giving a clockwise torque, that will be mg times x, right? And also the tension that gives a counterclockwise, that will be t times sine theta times 1. Okay, all right. So basically, what is tension here? We've already calculated that, right? Let's find that here. Where's the tension? Calculate tension here. This is the tension, right? So we basically move that here, mg times x minus mg times x divided by sine theta times sine theta, right, times 1. Okay, what is that? This cancel out, right? That will be mgx minus mgx. This final torque that's using the left end as the reference point will give you 0. This basically verify that we have done all the calculation correctly. Okay, so basically no matter which reference points you choose, all of the force, the torques of all of the force, when you add them up together, they should give you 0. All right. One more thing I want to add is that here in this calculation, we consider that this meter stick is massless, right? So basically, we didn't consider the weight of this meter when we were calculating this problem. However, if it has a mass of m, then we need to include um, the weight of this meter into this picture. That is, we have to consider the weight force of this meter that comes from the center of gravity. That's basically the midpoint of this meter, and it points down. Okay, that will be the big M times G. And if we consider that, the result will be slightly different. But all of the calculation, the equation that we use remains the same. Okay.